the testing. I'm Tingsu from ETH Zurich. Today, the first presentation will be from Luis Cruz on the energy footprint of mobile testing frameworks. Now it's your turn, Luis.
Hello, everyone. Sorry. So my presentation is on the energy footprint of mobile testing frameworks, and this is a work I've done with my previous supervisor, Rui Abreu. And the work was published at Transactions on Software Engineering. The idea is that for energy testing, we need to first create an automated interaction with the app. Then we need to collect energy measurements and compare the results with the baseline, typically the previous version of the app. And the thing here is that we want to understand whether creating the automated interactions is actually affecting the results of our energy tests. So typically, to create an automated interaction, mobile developers resort to APM, Calabash, Espresso, Monkey Runner, and all these sorts of automated testing that may have some energy overhead on the tests. So I'll give you an example. We have two versions of the same app, and there's the original version and there's the optimized version. And developers want to understand whether the optimized version has more or less energy consumption than the original version. And to do that, they have to create a test, an automated test for the original one, and another automated test for the optimized version. And these tests are slightly different. The first one has a single scroll, and the second one, the optimized version, the test has a scroll and several tabs. And what we want to understand is if these automated interaction tests are actually affecting the results of the energy tests. So here's what we've done. We went to all these different automation frameworks, Android View Client, IPM, Calabash, whatever, and we created a test for taps, for long taps, for swipe, for all these user interactions that you might have in a mobile application. Then we ran the scripts, collect and compare the energy consumptions between all these different frameworks. And here are some of the results we have in our paper. So we can see that the energy consumptions of a single tap are quite different depending on the framework that we may use. And we can see some very different results. You can see, for instance, that comparing with the human interaction, APM is actually spending 9 times more energy, or Calabash is spending 5 times more energy. And this may affect the results of the energy test. They may make the energy tests unreliable. So in the paper, you can see the same thing for find by ID, drag and drop, back button, swipe, and all these different interactions. And we make comparisons and we discuss some of the implications of it. So here are the main takeaway messages that we got in the paper. So we need to select the best UI automation framework. Otherwise, we may have the wrong energy test results. We need to select elements in the UI based on their ID and not on their content. And to understand more what I mean about this, you really need to read the paper. Also, we found that this poor energy efficiency of these automation frameworks are not because they are not good quality, it's just because they are not made to do energy tests. We also found that some previous studies in our community may have wrong results, or they may not have found statistical significance on their energy optimizations because of the framework they were using. And finally, we make some advice on which framework should be used depending on the project. So please check out the paper. Here's the QR code, there's the DOI. And if you have any thoughts or questions, I'm happy to take them. Thanks.
Okay, so thanks for the presentation, Luis. So now it seems we do not have question of Slito. So I have a question about your presentation. So from your experience, how for the practitioner to balance the expressiveness of these testing frameworks and the energy consumption? Do you have any insight on this direction?
Sorry, I didn't understand the first part of your question. Could you repeat it?
Okay, so because you compare different testing frameworks, so these frameworks have different kinds of test scripts. So some test scripts are more easy to understand. Some test scripts maybe use different APIs. So from your observations, what's the difference of these?
Yeah, there's one big difference, and for me it's quite important, which is some of the scripts are actually very readable, and they also allow you to easily interact with the application while you're writing the test script. And other frameworks require you to first write a test script, then compile it, and then send it to the phone and run it. So they do it more or less offline, and that's quite cumbersome to do. Because when you're writing a test, it's a very experimental process. So these kind of things are actually important. And one cool thing about it is some of the most readable frameworks are actually also energy efficient. So it doesn't mean that to have an energy efficient framework, you need to have a very difficult process to create the tests. It's not related to that.
Okay, thank you. So how do you have any other suggestion to the industry practitioners when they using these testing frameworks when they want to measure the energy?
Yeah, so I think the main advice I'd give would be to first, so most of the times you should use Espresso. Espresso is the most energy efficient framework. But if sometimes you feel like it doesn't really meet your testing requirements, you may look into the paper and check all the other testing frameworks, because depending on the case, you may have better or worse options. So this is not a black and white decision. It's actually, it takes a lot of details before selecting the framework.
Okay, thank you. So the time we need to transition to next speaker. Thank you.
Thank you.
So next speaker will from Jue Wang. He will talk about how to generating high quality test inputs for Android apps. So now it's your turn, Jue Wang.
Okay, thank you. Okay, hello everyone. I'm Jie Wang from Nanjing University. Today I'm here to talk about our work for generating high-quality test inputs for Android apps via use case combination. My co-authors are Yan Jiang, Changxu, Chuncao, Xiaoxingma, and Jianlu. Our work is about Android app testing, but first, let's talk about boxing. Boxing is like one of my favorite sports. During a boxing match, a boxer throws punches aiming to attack weak points of the opponent. However, these weak points are often well protected. So how can the boxer land a punch at the weak point? Normally, the boxer does so by conducting a sequence of standard moves. For instance, he can first throw a jab to draw attention, then a left uppercut to throw off the balance, and finally a cross to hit a weak point. Such a sequence of standard moves is called a combo. Now, when you think about it, boxing is not that much different from Android app testing. Think of one boxer as the tester and the app on the test as his opponent. Now, the tester attacks aiming to manifest potential bugs with test inputs. However, just like the weak points, bugs are also well protected. They are often hidden deep in complex functionalities. Let's see a real example of AARD2, a popular dictionary app. User can add local dictionaries by clicking Find Dictionary buttons on the Dictionary tab. After the dictionary is added, user can go to the Search tab, search for a word, and click a result via its detail. In the detail page, the user can also click the star button to start word for future review. Now, at any time, if the user no longer needs a dictionary, he can always go back to the dictionary page and delete it. All the words of the dictionary will be deleted and can no longer be searched. However, if the user has started a deleted word, he can still find it in the Start Word tab, and by clicking it, the detail page still shows with nothing displayed since the content has been deleted. In the detail page, the user can choose to zoom in the page for a better look. However, since now the content is null, clicking the zoom in button crashes the app. As you can see, to manifest this bug, we need a test input with certain events exercising 8 functionalities in specific order, including entering the same page multiple times. Existing automated tools are unlikely to generate such long and meaningful test inputs. Random or heuristic techniques are like angry but amateur boxers who quickly land random punches, i.e. test inputs, and therefore unable to reach deep states. On the other hand, systematic input space exploration techniques are like Einsteins with boxing gloves, who always do heavy calculation before each punch, and therefore suffer from scalability issues. So how can we generate such long and meaningful test inputs in a scalable fashion? In a boxing match, the boxers often conduct a combo of moves to attack weak points. A long and meaningful test inputs can also be decomposed into moves represented by functionalities they exercise. Therefore, such a test input can also be regarded as a combo, a sequence of use cases that manifest designated functionalities of that. Conversely, we can utilize use case combination to generate long and meaningful test inputs, which we call combos. This is the ComboDroid framework we propose. Given an app on the test, we first obtain various use cases. Then we enumerate combos by concatenating use cases in specific orders. Moreover, we can always go back to the first phase when we need more use cases. Let's discuss each phase. The first phase is to obtain use cases. The first observation made is that each use case always begins and ends as quiescent app states, where the app is idle or stable GUIs. Therefore, given an execution trace of the app, the event sequence of each subsequence beginning and ending at quiescent app states can be extracted as potential use cases. Now the question becomes, how can we obtain execution traces, and which subsequence of the traces we should select? The first option is that we can always turn to human for help. A human can use an app as normal to easily generate sufficient execution traces. Moreover, since a human can easily understand the semantics of the trace, he or she can quickly annotate the trace to select use cases for extraction. Meanwhile, automated testing techniques can generate execution traces containing fragments of use cases. In our ComboDroid framework, we implement a DFS-like state space exploration tool to provide such traces. Then the use cases can be mined with an extended labeled transition system, where each state is an abstracted state GUI state, and each transition is triggered by an event. With this model, we connect subsequences that can compress a use case, such as the 2 transitions in red. Finally, we extract each acyclic path from the system as use cases. Note that these 2 flavors can also mix up according to the tester's preference. With the use cases, we can then enumerate use case combos to manifest potential bugs. Since use cases are short event sequences, any use case sequences can be a valid test input. However, it's not necessarily a combo, i.e. not long and meaningful. For example, suppose we want to directly concatenate these 2 use cases. This will be confusing because the event of the second use case cannot find the proper receiver as the end state of the first use case, and thus cannot properly exercise the designated functionality of that. This makes the combo meaningless. Therefore, we need to ensure that each use case can properly manifest the functionalities of the app. We do so with aligns with relations between use cases. A use case aligns with another if we witness at least once in the execution trace that the first event of the second use case is successfully delivered to the app as the end state of the first use case. Otherwise, they are not aligned. Now, by ensuring that each consecutive use cases in a combo are aligned, each use case is very likely to manifest designated functionality. Now we have made sure that our combos are meaningful. For better testing performance, we also want to maximize data flow diversity so we can exercise different behaviors of that. We do so with depends-on relations between use cases. Given 2 use cases, the first use case reads some shared. If the first use case reads some shared program state like the database, and the second use case reads it, then the second use case depends on the first one, which is an indication that if these 2 use cases are combined together in a combo, the second use case is likely to access different behavior of that. Therefore, we want such relations exhibited in a combo as much as possible. With the 2 relations, we can enumerate meaningful combos accessing different behaviors of that. Given a set of use cases, we first infer their depends-on relations. Next, we sample combo skeletons from the use cases. These skeletons must exhibit sufficient depends-on relations to ensure data flow diversity. Then we infer aligns with relations from the use cases. Finally, for each combo skeleton, we insert use case sequences into them to ensure the alignment of consecutive use cases. Each of these use case sequences is obtained by searching in a DFS manner in the aligns with relation graph. Sometimes exercising a new behavior of the app can lead to a previously unexplored state, and the functionalities concerning this state have no use cases to manifest. In this case, we return to the first phase, obtaining new use cases concerning this state, and then proceed to continue enumerating combos. we have conducted thorough empirical evaluation of ComboDroid. We implemented two variants of the tool: ComboDroid Alpha, which obtains use cases fully automatically, and ComboDroid Beta, which relies on human to generate execution traces and annotate use cases. Moreover, we selected 17 real-world Android apps as test subjects to evaluate the performance of a tool. They are either used to evaluate existing works or popular on GitHub. For ComboDroid Alpha, which is a fully automatic variant, we compare its testing thoroughness with the three existing automated tools, where Sapiens and Ape are state-of-the-art, and the Monkey is the state of practice. We compare the Baejke instruction coverage achieved by each tool on each subject, as well as the bug manifested by them. For coverage, ComboDroid Alpha achieved the highest coverage ratio on 16 out of 17 subjects, which is averagely 4.6% higher than the best existing techniques Ape. Note that this is already twice the improvement of Ape over Monkey. Moreover, according to the progressive coverage plots, ComboDroid Alpha continuously gain additional coverage when others converge early in the process. For the bug manifestation, ComboDroid Alpha successfully manifested 11 out of 12 reproducible bugs, where Ape manifested only 7, which is the best of existing work. Moreover, ComboDroid Alpha manifested 4 previously unknown bugs, where only Ape manifested 2 of them. All these bugs have been confirmed and 2 have been fixed. With this result, we are safe to say that ComboDroid Alpha is more effective in automated generating high-quality test inputs for Android apps compared with existing techniques. For ComboDroid Beta, which is a semi-automatic variant, we compare the testing thoroughness with an Android testing human expert. This ComboDroid Beta relies on human to obtain use cases. It teams up with a recruited tester. We give him 1 workday, which is about 8 work hours to generate use cases. Then we give ComboDroid 12 hours to enumerate combos. Meanwhile, we give another human expert 3 workdays, which is about 24 work hours, with full access to the source code in order to maximize coverage. We selected the 10 largest subjects for this evaluation and measure only coverage. The result shows that though the human expert achieved the highest coverage, averagely 12% higher than ComboDroid Alpha, ComboDroid Beta achieved a comparable coverage with its expert, only 3.2% less in average, and outperformed human for an app. Furthermore, from the result, we found that enumerating combos indeed greatly amplify the effect of use cases, gaining 13% more coverage in coverage. In conclusion, ComboDroid Beta demonstrates the potential of automatically leveraging human insights in completing and boosting automated techniques. So in a short summary, manifesting bugs hidden deep in Android apps often require long and meaningful test inputs, which existing automated tools are unlikely to generate. We propose the ComboDroid framework that generates such test inputs by enumerating combos of use cases that manifest designated functionalities of the app. The empirical evaluation results show that both the fully automatic variants and the semi-automatic variants achieved promising performance. The ComboDroid tool will be released publicly this summer, so please stay tuned. This ends our presentation. Thanks for listening.
Okay, so thanks for Jay's presentation. So we have no question yet. So I have one question that when you talking about how to generate the use cases, you have 2 variants. One is generated by a human, another is generated automatically. So have you considered combining these 2 variants together? Do you foresee their effectiveness will be better?
Yes, the combination is of course available. As I said, the 2 flavors can mix up, i.e. the execution trace generation as well as the use case extraction can combine with using different approach, either manually or automatically. For the effect, I'm not coming up with any conclusion yet, but I'm thinking if we combine it, it is going to be better with a better automatic approach, I think.
Okay. So in the results, we see that sometimes Monkey can find some additional bugs. How do you explain this phenomenon?
Monkey can find more bugs for our evaluation. It's because that there is one app is called drawing. It's a drawing app that you can draw something on a paper, which is not widget-based. For Ape and ComboDroid and other many state-of-the-art tools, we use widget-based event generation. But for like something like drawing apps, they are not widget-based, so we cannot generate proper events. Therefore, we cannot generate proper use cases or any test input sequence. Therefore, but on the other hand, Monkey is able to generate any testing event. So therefore, it can discover additional bugs.
Okay, so thanks for your explanation and your presentation, Jeff. So now let's move on to the next talk from Nancy Cooper. He will talk about how to translate video recordings into replayable scenarios. This also received a distinguished paper award.
Hi, everyone. My name is Nathan Cooper, and today I'm going to be presenting the paper Translating Video Recordings of Mobile App Usages into Replayable Scenarios. So video recordings of mobile app usages has a wide variety of use cases. The one I'm going to be focusing on in this presentation is video-based bug reporting. Here are 3 examples where each video denotes the steps in order to reproduce a particular bug in the application. Now this can be extremely useful if you have a team of testers or end users that are committing these videos to an issue tracker such as GitHub or GitLab, where a team of mobile developers can then take these videos to review. However, this can quickly get out of hand with the sheer volume of videos due to the manual nature of having to review these videos to, say, reproduce the particular bug present in them. That's where V2S comes in. V2S stands for Video to Scenario, and it's an approach that takes a video of mobile app usage and generates a replayable script that can be reran on a physical device or emulator that replays the exact steps present in the video. V2S has 3 phases. The first phase is all about determining where in the video and on the screen the user interacted. We first deconstruct the video into its constituent frames using FFmpeg. Then each frame is further analyzed by locating where in the frame the user interacted. To do this, V2S requires a particular developer option to be enabled that visualizes the touches that the user performs with this white circle. In order to localize where this white circle is in the frame, we use a deep neural network called the Faster RCNN Object Detection Network, where it's fed through a CNN model and ran through a region proposal network, as well as some other additional steps in order to predict where in the screen the user's clicking. To train this model, we generated an automated data generation pipeline where we use a previous data set from a previous research called Redraw that has a diverse set of GUIs from a wide variety of applications, where we superimpose this touch indicator randomly on these screenshots. This allows us to generate a plethora of data for a wide variety of backgrounds and use cases so that our model can be robust to different sets of applications. Next, we have to determine the state that this touch indicator is in. It has 2 main states. One where the finger is actually touching the device, so the opacity of this visualized touch indicator is at its fullest, and one when the user is pulling their finger away from the screen and it's slowly fading away. We need this information to disambiguate some of the more complex cases, such as when a user is typing really fast or doing actions very fast in the video. To do this, we use a CNN that's based on an AlexNet architecture that has a binary classifier for whether or not the finger's touching or the finger's lifting away. And the training data is generated in an automated fashion similarly to the object detection network, where we take random crops of the redraw dataset and superimpose the touch indicator at varying levels of opacity. The next phase then takes these touch indicators throughout the different frames in the videos and groups them and classifies them into high-level actions such as taps, swipes, and other gestures. To do this, we model the problem as a graph problem, where the nodes are the touch indicators and the edges connect touch indicators that belong to the same action. In order to do this connection, we use a modified connected components graph algorithm with a few heuristics for how the connections are made. First, we only connect to an immediately successive frame. So a touch indicator at time t can only connect to a touch indicator at t plus 1. Also, we never connect from an ending node where the finger is being lifted to an active node where the finger is touching. And additionally, if there's multiple options such as in t plus 2, we pick the node to connect to that is the closest in distance. For the action classification, we have some main heuristics that we use, which is if the touch indicator through the life cycle of the action didn't move more than 20 pixels, we consider it a tap or a long tap, and everything else is a gesture. And we classified taps and long taps as just the how long the action lasted. Phase 3 then takes this action segmentation and classification and converts it into the low-level commands that your device needs in order to replay the events on a physical or emulated device. These are then offloaded onto the device and reran using a previous research tool called reran. To evaluate our approach, we had 5 main research questions, but I'm only going to be discussing 2 of them today. The first, we had 2 main user studies in order to determine the accuracy of the replays that V2S was able to generate. The first study had 8 participants from our college where we gave them 20 applications and asked them to either reproduce a real bug, a bug that we inserted, or to generate a natural scenario of the application. The second study used 3 of the authors where we selected 64 applications from the categories in Google Play. We used a wide variety of metrics, and here are some of the performance for the precision recall of V2S. And so overall, the precision recall for V2S is 95% and 98% respectively. And overall, V2S was able to successfully reproduce a total of 96.67% of the bugs and crashes and 91% of the natural scenarios faithfully. For RQ5, we interviewed 3 mobile developers from Google, Proximus, and 7-Eleven. We took the application that they worked on, generated our own videos from them, fed them through V2S, and recorded the replay that V2S generated and interviewed them. Here are some of the responses. So on usage data, V2S could collect the types of interactions, number of tabs, etc., to detect, for example, if certain screens are frequently used. Another developer said V2S could be potentially useful for helping to replicate hard-to-reproduce bugs. And overall, the perception of V2S was high among the developers. In conclusion, I've discussed the motivation for being able to automatically replay mobile app usages. I discussed the approach V2S attempts to solve this problem. And I discussed the evaluation that we performed of our approach. And we have a particular website that you can reach at this URL. And thank you very much for your time. If you have any questions, I'd be happy to answer them.
Okay, so thank you for the presentation, Nathan. We have one question from the audience. The question is, in practice, why end users would be willing to allow recording their own interaction with the apps? Can you hear me? Listen?
Sorry, can you hear me now?
Yeah, I can hear you.
Okay. So for end users, the scenario for end users would most likely be a case where they are trying to reproduce a bug. So if the app crashed, the particular application may ask the user to record the scenario for them. There may be other scenarios where they have some sort of compensation for recording different scenarios, but in general, for end users, it's most likely going to be for bug reporting.
Okay, so another question is, what was the size of your training data set?
So the training data set was 50,000 screenshots that was split into training and testing, 70-30 split.
Okay, so I have a question. So do you have any limitation on you translate the human touch if the human use more than one finger, like some zoom in or zoom out?
So right now, V2S does not handle those situations. We are currently working on expanding the amount of gestures that are supported. So we now are working on 2-finger gestures such as pinch to zoom, and rotations, and as well as handling other gestures such as 3 fingers or 4 fingers. However, in our evaluation of the applications, the only main actions that were really useful were swipes, clicks, and long taps, which is why we settled for those during this work.
Okay, thank you, Nathan. So we will move on to next presentation from Bruno. He will talk about an empirical study of quality of Android application written in Kotlin language. Now it's your turn.
Okay. It's okay. So hello, everyone. And good morning, good afternoon, good evening. So my name is Bruno. Today I will present my research, an empirical study on quality of Android applications written in Kotlin language, which was published in Empirical Software Engineer. So in the past few years, we are observing an explosion of the popularity of mobile device and mobile applications. In this context, Google has 70% of the global market share for mobile operating system, and last year, Android has overcome Windows and become the leader of the market share for operating systems. Regarding applications to download, we can find more than almost 3 billion applications on Google Play, the official Android store. Historically, since the first release of Android in 2008, applications were built using Java. But this changed in 2017 when Google announced Kotlin as an Android official programming language. Kotlin, which was created by JetBrains, is a programming language that combines object-oriented and functional features. And it runs on the top of the Java virtual machine. So it means that Kotlin and Java, they share the same bytecode. And because of this feature, Kotlin is fully interoperable with Java, which means that you can call Kotlin code from a Java file and vice versa, even in the same app, in the same project. So we can have as little or as much Kotlin in our project as we want. So basically, we have 2 goals in this study: to measure the adoption of Kotlin by Android developers, and to measure whether Android applications written in Kotlin have a better quality than applications written in Java. So regarding the first goal, we answer this following research question: what's the degree of adoption of Kotlin mobile Android development in our dataset? So to answer this research question, we collected applications released from 2017 until the date of this work. We collected their source code and the code repository and their binary file, the APKs of each released version. Then we built a process to classify applications to filter Kotlin applications. So we split our applications in applications written in Kotlin and applications written in Java. The last one doesn't have any Kotlin code. And to do that, we combined 3 source of Android applications: F-Droid, Android Time Machine, and Android Zoo. We collected a total of 2,167 applications and their repositories, and more than 17,000 APKs, the binary files. So we found that 244 out of 2,167 applications, around of 11%, have at least one version written totally or partially using Kotlin, as we can see in the plot. We also answered 2 more research questions, but for sake of limitation of time, we are not targeting this presentation. What's the proportion of Kotlin code in mobile application? How does code evolve along the history of Android application after introducing Kotlin? Regarding the second goal, we answered this following research question: how frequent does the introduction of Kotlin possibly impact the quality of the version of Android application? Positively impact, sorry. So to compare the quality of Android applications, we consider the occurrence of code smells. Code smells are code that can be refactored to improve the maintainability of our software. So to find those code smells, we use a static analysis tool named Paprika that works at the level of bytecode. So this is important because looking at the bytecode, we can compare Java and Kotlin fairly because they share the same bytecode, that is the bytecode used in the Java virtual machine. So in this study, we considered 10 code smells, 4 object-oriented code smells, and 6 Android-specific code smells. We use a linear regression model for scoring the quality of each version from a mobile application. This model received as input the number of code smells and the size of the application, and as output, we got a score where a high score means better quality. So this score serves as an estimation of the mobile app quality in a particular version. So we found that the introduction of Kotlin in Android application initially written in Java produced a rise in the quality scores from at least 50% of applications of our dataset. And here in the plot, we can see an application in Mozilla Clar, where Kotlin was introduced in the 6th release, and then you cannot see the increase of the quality in the following versions. So as conclusion, we conclude that Kotlin reached a remarkable adoption around 11% and after became an Android official programming language. And also we saw that applications written in Kotlin, the amount of Kotlin tend to increase at the same time the amount of Java tend to decrease or remain constant. Also, we found 50.8% of applications migrated completely. And finally, the introduction of Kotlin on Android applications may produce a rise in the application's quality. That's it. Thank you everyone. Any questions?
Okay, so thanks for presentation, Bruno. So now I have see some questions from the audience. So in your talk, you mentioned you use one static analysis to analyze the code smells. So, but there are a lot of static analysis tools out in the wild. So have you ever considered other static analysis tools to measure measure this problem?
Yes, actually, during this study, this was a concern because, especially in Java, we have a lot of static analysis tool. In Kotlin, we have less, maybe 2 really popular one, but we decided to use this one, Paprika, because it works in the bytecode, so they compare fairly both applications. Because if we pick one to analyze Kotlin code and a different one to analyze Java, maybe we could have different ways of evaluating the same code smells, or how they collect the same code smell could be different. So we consider that, but we conclude that Paprika was our best option. But we can target this also.
Okay, so we have one question from the audience. The question is, your method covers 6 Android code smells. Does the method cover any secret code smell? If so, which secret code smells are covered?
No, we are not targeting any secret code smells. Basically, they are code smells related with some specific entities of Android activity, some broadcast receivers, but we didn't consider any security code smells.
Okay, so thanks for your presentation, Bruno. So we will transit to next presentation. So next presentation. Okay. So we're from Gianluca. He was talking about enhancing trustability of Android applications. So now it's your turn.
Yes, hello everyone. I am Gianluca Scoccia from the University of L'Aquila, and I will present our work enhancing trustability of Android applications via user-centric flexible permissions, which appeared on the IEEE Transaction on Software Engineering journal. So the context of our work is that of Android permissions, and we believe that the current Android permission model suffers from a number of rigidities. In particular, these are the granularity of its permissions, which are too broad, the timing at which the permissions are granted, and the fact that it considers all users as equal. So there is a limited customization that the user can do on the permissions it grants. So basically, based on these facts, we believe that it neglects the user rights to express their desires when granting the permissions. So to address these issues, we designed an alternative permission system, which is AFP, Android Flexible Permissions, that introduces the concept of feature-based and level-based permissions. Feature-based means that the permissions are not granted monolithically to the entire application, but are given to individual app functionalities. And level-based, that the permissions are not restricted to Boolean values, but if the underlying resource allows it, we can have other values. For instance, if you consider the GPS position, you can grant it, deny it, or you can also grant it, but with a certain degree of precision. What we have done is to define a process that allows developers to introduce these permissions into their existing apps. And to do so, we provide developers with an automatic tool to define what are the features offered by their app. And then we use static control flow analysis to introduce the new permissions into the developer application. So it's all automated. And on the other side, the user can configure the new permissions using an ad hoc app on his phone. And finally, the permissions are enforced at the runtime. So we evaluated our approach performing 4 experiments, and we wanted to evaluate these 4 aspects, so performance, usability, acceptance, and trustability. And in our evaluation, we involved both end users and developers. And the full detail of the evaluation are in the journal paper. I will only present a few highlights. So the first experiment we have done was with the developer acceptance. So are developers willing to adopt our approach? And to answer this question, we asked some developers to try out our tool to define the features of their app on some of their applications. And we asked them to complete this task because it's the only one they have to do manually. All the rest is automated. So as you can see from the picture, we afterwards that they tried out our tools, we collected their responses with a questionnaire. And as you can see, the responses were mostly positive. So the feedback we received was mostly positive. And the developers understood how the new permission work. And most of them stated that they would be willing to use them into their future applications. Similarly, we conducted an experiment to assess if the end users are willing to use the new permissions we propose. And in this case, we asked the end users to try out some applications using both our AFP system, but also the standard Android permission system. And afterwards, again, with the questionnaire, we collected feedback from them. So as you can see, also in this case, our AFP approach received positive feedback. The users understood how the new permission work, and they stated that they would be willing to use them in their day-to-day use. But also, we can see that in general, our approach received better scores than the Android standard permission system. So users were more pleased with our AFP approach. In the same experiment, we also measured the usability from the end user's point of view. And to do so, we used a standard set of questions that is called the system usability scale, that is used to assess usability of a system. And you can see the results of this evaluation, and you can see that also in this case, the users found that the usability of our approach was quite good, so it was more than acceptable. So this concludes my presentation, and of course, I had to leave out a lot of details and just present a few highlights. But we are available at the following email addresses if you have any questions or comments or are interested in this project. And thank you for your attention.
Okay, so thanks for your presentation. Up to now, we do not have questions from the audience. So from your talk, you discussed the problem of trustability. So for Android platforms, there are actually different versions. So do you observe any discrepancies or some problems about the trustability?
Yes, so there are a few different versions of the Android platform, as you said, but there are mainly two versions of the permission system, one that is at runtime and one that is instead at install time. We compared our approach to the most recent one, so the runtime one. And we discussed this better in the paper, but the current Android permission system has some issues about the trustability because you don't know what the developer will do with the permission you grant. So they can ask it for something, but then use it for everything. And instead, what we do is restrict the permission to a specific feature of the application. So you grant it for that feature, and it's limited to that task alone. So they can only perform that task with that permission. So this is the way we try to address this issue.
Okay, so thanks for your answer. That so you handle this problem. So do you think it's possible to automatically generate some proof of concept or some test inputs that can prove the existence of this kind of trustability issue?
Maybe we didn't focus on testing in our work, so we focused more on the user aspect, so the usability and the trustability and the acceptance. So we didn't specifically work on the testing. We right now we have the developer has to provide us some information, which is the features provided by his application, and we are trying to automate also that step, and we are working on this topic now.
Okay, so thanks for your presentation. So we move to the next presenter. So next presentation will be from Hassan. He will talk about longitudinal study of popular ad libraries in Android apps. So now it's your turn.
Can you hear me?
Yes.
Okay. Hello, everyone. I am MD Hassan Zaman. I am a PhD student, and my supervisor is Professor Hamid Hassan in SAIL Lab in Queen's University. Today, I'm going to present my journal work paper where we study the evolution of ad libraries in Google Play Store. So majority of the apps in the Google Play Store are free to download. That means users do not have to pay any money to install and use this application. Although these apps are free, app developers can earn revenue through in-app advertising. In this model, app developers display ads on mobile devices, and when users interact with this app, for example, clicking on these ads, app developers can earn revenue. According to recent research of App Annie shows that in-app advertising is a growing market, and it was forecasted to about $200 billion by the year 2021. Now let's take a look on how in-app advertising model actually works. Business companies such as KFC has contracts with different ad networks, for example, Google. Each ad network provides a special library, which is called ad library. In order to display ads on mobile devices, app developers have to integrate this ad library into their apps. The main functionality of the ad library is to serve advertisements from different ad networks and display these ads on mobile devices. So when users install and use these applications and interact with these ads, app developers can earn revenue. That means that ad library plays an integral part in mobile app ecosystem. To earn more revenue, app developers integrate many ad libraries. Our study shows that 57.9% of the studied apps integrate more than one ad library, and the number of ad libraries could reach up to 19 ad libraries. Integrating multiple ad libraries could cause some issues. One of the major issues is that integration of many ad libraries increases the overall app size. Our study shows over 18 months of historical data of mobile apps shows that app size increases by 10% because of ad libraries. So research shows that when the size increases, there is a negative impact on app popularity. And another issue is that the maintenance challenges, for example, selecting an ad library for displaying advertisements. Therefore, in this study, we focus on two important aspects of ad libraries. We study how ad libraries are evolving over time and how do ad developers integrate multiple ad libraries. For our study, we select apps from Google Play Store and we identify 8 most popular ad libraries. we downloaded all the release notes and the jars, and we studied them. And these jars covered almost 33 months. So we studied the evolution of ad libraries along three perspectives. We studied the binary size of the releases. We tried to understand the reason for releasing a new version of ad libraries. And we also studied the architecture of ad libraries. We identify 4 trends in the evolution of the binary size of the studied ad libraries: explosive growth, stable growth, shrinkage, and fluctuating size. We observed that the library developers try to reduce their ad library size by modularizing the overall architecture of their ad libraries. We identified that video streaming ads is the main reason for releasing a new version. We identified 4 main features related to video streaming ads. One is offering rewarded video ads, adding video control, for example, start and stop a video advertisement playing, and handling native video ads so that displayed ads has the same app context with the app context, and prefetching video ads that reduces the overall load time of displaying the advertisement. Finally, we derived a reference architecture of ad libraries, which mainly consists of 5 main components. The main component is the ad lifecycle manager. It retrieves user data using analytic components and retrieve advertisement for using ad retrieval components. With the both information, ad lifecycle manager then display image ads or video ads on mobile devices. All these components relies on some utility functions. So in summary, we observe that ad libraries are actively evolving over time, and our derived reference architecture of ad libraries can serve as a template for creating a new or evolving an existing ad library. Now, we also study the integration of multiple ad libraries in mobile apps. We observe that integrating multiple ad libraries has a positive correlation with the number of downloads of an app. We identify 4 common strategies for integrating multiple ad libraries. And based on the comparative study of these strategies, we observe that ad library developers still need better support for integrating multiple ad libraries. More details about the integration of multiple ad libraries are available in our paper, which is published in CSE. So in summary, ad library plays an integral role in mobile app ecosystem. We study the evolution of ad libraries and the integration of multiple ad libraries. We observe that ad libraries are actively evolving over time, and our derived reference architecture can be useful for creating or evolving an existing ad library. And we also observe from the integration study that ad library developers still need better support for integration of multiple ad libraries. So thank you very much. This is MD Hassan Zaman. Feel free to ask me any question, and here's my email. You can contact me. Thank you.
Okay, so thanks for the presentation, Hassan. So up to now, I have not seen questions from the audience. So from your presentation, you mentioned you explore the ad libraries from different apps along within a long history. So how do you do that? You have some automatic way to dynamically explore the app or do some static analysis? Can you give more details?
Okay, so we downloaded all the history of apps. We actually downloaded 1,840 apps and 35K updates of these apps in Google Play Store. Then we identify the top most popular ad libraries. So we basically focuses our study on 8 most popular ad libraries. So for this study, we study the release notes of these ad libraries and the jars for these ad libraries. So we used understand tool to do some static analysis so that we can generate some concrete architecture for these ad libraries. That's how we derived a reference architecture for these ad libraries.
Okay, I understand. So yeah, so you talk about many findings from the perspective of functionality of these ad libraries. So have you ever considered that there are some security evolution of these ad libraries? Like some ad libraries may, at the beginning, they want to push a lot of aggressive notification to solicit the users to download some malware or something. Have you ever considered in this direction?
So from this release note, we identified some updates. So they do some updates for ad libraries for security reasons, for example, GDPR issues. So for security. And also they mentioned that some add libraries actually reduces some permissions so that app developers and app users doesn't have any concern. So we found some reasons or related to security and permission that why they actually releasing a new version.
Okay, so in the future, what kind of direction you can foresee that more research efforts should be put?
So one of the reasons is we found out that add library integration, especially multiple add libraries, has still some issues in mobile apps. So in future, based on our different architecture and our study on the multiple integration, add library developers can focus some improvement on how to they provide better support for integrating of multiple add libraries.
Okay, so now the time is end. So thanks all the speakers. So our session ends now.
Greetings, everyone, and welcome to the Android and web testing session. So we have a very interesting line of presentations today in this session, including 2 demo teasers and 4 technical papers. Please note that there is a delay between the actual presentation in the Zoom room and the ones you see in the Clouder. So if you have any question, just don't wait until the end of the presentation to ask. Also, you can ask your question in the Slido panel in the left side, and you can chat during the presentations in the right panel. So with that said, we are starting with Farnaz Behrang from Georgia Tech, who is going to present a tool for automated test migration for Android apps. So there is going to be a pre-recorded video, but Farnaz is here to answer your questions at the end of the presentation.
This is Farnaz Behrang, and I'm going to present our demo paper, App Test Migrator, a tool for automated test migration for Android apps. As you know, there are tons of existing mobile apps in the market, and if you look at these apps more carefully, you can divide them into different categories where the apps that belong to each category share much of their functionality. So App Test Migrator takes advantage of this situation to improve the way that we test these mobile applications. So instead of creating brand new tests for each application, App Test Migrator tries to migrate test cases from one app to all other existing similar applications. So the overall goal of App Test Migrator is to migrate test cases between apps that share at least part of their functionality. At high level, App Test Migrator takes as input a source app, a set of source tests, and a target app, and as output, it generates a set of target tests. So given the source test, it first instruments the test, and it then runs this instrumented source test and records a sequence of GUI events that are triggered and assertions that are checked by the test. Once it collects them, it continues by migrating first the GUI events and then migrating the oracles. And finally, it generates the test scripts with these migrated GUI events and oracles. Our implementation of App Test Migrator supports Android apps, as Android is one of the major platforms in the mobile app market. The technique requires as input tests written using the Espresso testing framework. We also modify the Espresso testing framework to collect relevant dynamic information during test execution. For our static analysis, we leverage Gator, a static analysis tool that creates a model of the GUI-related behavior of an Android app. We also use Neo4j, a graph database management system, to interact with the static model. And to generate our word-to-vec model, we use GenSim, an open-source vector space and topic modeling toolkit implemented in Python. For more information regarding the technique and its implementation, you can check out the tool's website. Thank you.
Thank you, Farnaz. So I don't see any question here, but I have a question for you. What kind of oracles the App Migrator supports?
Sorry, can you repeat the question?
What kind of oracles the App Migrator supports? Is it just like traditional kind of assertions, like for checking the null pointer exceptions, things like that, or is it related to Android presence of some widgets, icons, things like that in there?
Okay, yeah. So there's sort of like a GUI oracles that are related to So basically the properties of the widgets on the screen. So it could be sort of any type of property. And also it supports the hierarchical oracles. So basically you can check the relationship between the GUI events. And also another type of GUI oracles it supports is those that it checks whether a particular GUI element does not exist in the particular GUI state. So basically 3 main categories of the GUI oracles that it supports.
Interesting. Yeah, thank you very much. Okay, let's thank Barnaz. Our second speaker is John Bell, who is joining Northeastern University in this fall, and we're all here because of his efforts. So he's going to present revealing injection vulnerabilities by leveraging existing tests. So please, John.
Great, thank you. So good morning, good afternoon, good evening, whatever time it is, wherever we are. In this brief talk, I'm going to describe our solution for revealing injection vulnerabilities in web apps by leveraging existing tests. So before getting to our approach, let me first describe an example of the kind of vulnerability that we search for. In this case, a SQL injection vulnerability. Now, a SQL injection attack occurs when an untrusted user input. In the example that you see here, the name parameter shown in tan, which is captured from a web form, flows into a command that is executed by a database without validation or standardization. In this example, an attacker can use apostrophes in their input to break out of the quoting on the name parameter, allowing the attacker to execute arbitrary SQL expressions, in this case, selecting all accounts from a table instead of just a single one. Now, I'm sure many of you watching this are saying, didn't we solve the SQL injection thing in the 90s? And also, how bad could a SQL injection attack actually get? Well, it turns out that in today's modern web apps, attackers can inject far more than just SQL code, which can lead to arbitrary remote code execution, which can be extremely devastating, as we saw just several years ago and are still paying for from this 2017 Equifax data breach, which was caused by a code injection attack on a Java web app. So broadly, we're interested in detecting code injection vulnerabilities. SQL injection was just one example of that, where an attacker-controlled input is executed by the database. We're also interested in detecting cross-site scripting injection attacks, where attacker-controlled inputs are executed not on the server, but potentially on every client's browser. And also, perhaps even the more dangerous kinds of injection attacks, like arbitrary Java expression injection, where an attacker could execute any kind of Java code on your remote server. So how do developers write code that's resilient to these kinds of attacks? The simplest example is by using input standardization. If we consider again the same SQL injection attack from just a moment ago, in this example, the malicious user could submit an input that included an apostrophe, which would break their input out of the quotes here and allowed them to execute this arbitrary SQL code. However, if instead of inserting those inputs from the user verbatim, apostrophes were escaped with backslashes, then the attacker wouldn't be able to break out of the quoted string and couldn't run their attack. Of course, that was a very simple example, but the same overall tactic of applying standardization and validation can be applied to all kinds of code injection attacks. So what should developers do to check to see if these validators and sanitizers exist and if they're vulnerable to these kinds of attacks? Well, on one hand, there are static analyzers for code injection detection that look for insecure data flows. But these tools can be tedious since they're prone to false positives and also to false negatives. Even state-of-the-art sound static analyzers like Julia are unsound when applied to real-world applications that use dynamic language features. And there are also usually manual steps, like identifying which methods correctly standardize input values, and again, investigating false alarms. Penetration testing, on the other hand, the dynamic dual of static analysis perhaps, aims to systematically attack the system and hence will have no false positive reports. But since it's a testing-based approach, it's impossible to be complete, it can take a very long time. Most worrisome is that penetration testing is such a long process because the analyst must often try these hundreds of inputs for every possible attack vector, trying strings like this. Not just these few, though. In fact, the suggested list of inputs provided by the industrial organization OWASP, just for testing for cross-site scripting and nothing else, contains over 200 different inputs that I just scrolled by the screen. You got to try those everywhere that someone could put in an input. Not a good time. So our approach, Rivulet, effectively performs guided automated penetration testing. However, of course, automated testing is hard, especially in applications that have complex workflows that must be followed in order to reach a vulnerability. Consider, for instance, a hypothetical healthcare application. The vulnerable component here shown in orange, used to message a healthcare provider about a recent telemedicine reading, can only be observed after logging in as a patient with telemedicine monitoring and submitting a valid but abnormal blood pressure or glucose level readings. It's extremely difficult for unguided test generators to satisfy this kind of workflow, generate these inputs and put these steps together to find that vulnerable component. So we focus on a better source of guidance. And that guidance comes from the test cases that developers have already written. These tests need not be security tests. Rivulet works by enhancing existing functional tests to also check for security properties. For instance, imagine that a developer who wants to test this application wrote a test called Test Message Healthcare Provider. That test might already expose this complicated workflow of logging into the app, entering some data, and triggering the message feature. Of course, the developer's functional test is simply asserting that there were no errors in the above steps. What Rivulet does is take this test and amplify it by using its embedded analysis to detect this component here might be vulnerable to code injection attacks, and then it tries to see, is it really vulnerable? Rivulet detects injection vulnerabilities by combining dynamic taint tracking and testing in a three-phase model. First, Rivulet detects candidate tests that might be used to detect security vulnerabilities by executing each of the original developer-provided tests using dynamic taint tracking. In this process, Rivulet intercepts every HTTP request as it arrives in the application server and taints each component of the request. When data arrives at a potentially vulnerable sync location, like the one that could execute code, Rivulet inspects the taint tags on those values to identify which, if any, of the user-controlled inputs flowed into it. In this case, perhaps we found that a cookie header was detected as flowing back to the user through an HTTP response, which could be exploited for a cross-site scripting attack. So then Rivulet will rerun those tests, modifying each test to try to inject those vulnerabilities and see if the vulnerability can be exploited. When it's rerunning these tests, if Rivulet detects that a tainted value flows into one of these sinks, it examines the entire context of the response being sent to identify if an attack really occurred. This step is important because simply seeing tainted data flow to a vulnerable method call doesn't necessarily imply an attack. In the first example here that I've shown on the slide, the attack string is contained in a comment, and hence it's not really going to be a successful attack. But when Rivulet generates an attack that defeats the comment, for instance, by breaking the comment, it can confirm the vulnerability and generate a one-click reproduction script to help developers investigate the vulnerability. We use the same approach to detect all kinds of vulnerabilities, all kinds of injection vulnerabilities. Briefly, recall that one of the limitations of penetration testing was that we had this humongous number of potential attack strings to test. So Rivulet condenses these inputs of cross-site scripting possibilities instead to just these 8 vulnerability patterns with several escaping rules. Rivulet leverages its dynamic data flow analysis to determine the precise context of a user-controlled input within the overall attack. For instance, in the example that I showed briefly on the past slide, Rivulet could identify that the session header is flowing into an HTML comment. It doesn't need to try to break out every kind of comment. It knows that it needs to just break out of that HTML comment, and it knows how to do that and do it quickly. We implemented Rivulet using our existing dynamic taint tracking system, Phosphor, which works entirely with off-the-shelf JVMs and applications without requiring access to source code and integrates easily with commonly used automated testing frameworks like JUnit and Maven. We evaluated Rivulet on several benchmark suites as well as on 3 open source web apps. Rivulet detected 6 new vulnerabilities in open source applications and significantly outperformed injection detection tools on benchmarks. Rivulet is freely available on GitHub, and my co-authors and I would love to talk to anyone who's interested in it. Thank you.
Thank you very much, John. I don't see any questions in Slido, but I have one for you. So can you elaborate more on the false negative that you got? I mean, compared to the alternative approach that you compared with, was it also false negative in that one, or how the false negatives were different?
Yeah, so Rivulet can struggle in cases where the vulnerability requires a really specific kind of value in order to reproduce it. The single false negative that we saw was in a case where the code injection vulnerability only existed if a random number was a one specific value. So there was a 1 in 2 to the 32 chance of detecting the vulnerability, but there was also only a 1 in 2 to the 32 chance of actually exploiting the vulnerability. So the static analysis tool would find that, but the dynamic one would not.
So we have questions from audiences. Andrew Habib, how do you find source things for the taint analysis?
Great question. So prior work has considered maybe higher level sinks, like say APIs for servlets, stuff like this. Instead, we set our sources and sinks basically just where sockets are. So we guarantee that we're not going to miss anything. So everything that's a source is everything that we read off of a socket, and everything that's a sink is everything that we write into a socket. For SQL, then we also look at SQL commands, and for remote code injection, we look at process that runtime.
Cool. One more question. So Michael Prado, next work, can you elaborate how the results of the taint analysis are used to select the malicious input?
Yeah, great question. It's one of my favorite parts, but was really tricky in this 8-minute talk to actually focus on doing this. So we use the taint analysis to determine exactly how we should build an input that is going to be likely to succeed in breaking through any standardization that exists. So in the example on the slide here, if we see that the tainted value flows into, in this case, it's like an HTML comment, it says debug : and then that input. We use the taint analysis to see that that tainted input flows into this HTML comment. Then we understand by parsing that entire response, that's an HTML comment, and then we can break it. Great. We do similar things with SQL and remote code. Yeah.
Sure, yeah, thank you very much. So our third speaker is Aziz Al-Shaiban from UC Irvine. And he's going to present the accessibility issues in Android apps, state of affairs, sentiments, and ways forward. Please, Aziz. You are muted. Aziz, you are muted.
Can you hear me now?
Yes, please.
Hello, everyone, and thank you for coming here today. My name is Aziz, and I am a member of the Software Engineering and Analysis Lab at UCI. Today, I'd like to give you an overview of our paper, Accessibility Issues in Android Apps. But before we begin, let's consider this scenario. So imagine that you wanted to send money to a friend, and you decided to use your bank app. So you downloaded the app, and then you saw this screen. So all you see here is button 1, button 2, button 3. So the only way to navigate the app, I think you agree with me, is just trial and error. So you would click on each one of these buttons until you find the screen that you want. Now, this is a much better version of the UI with labels that clearly define.
Sorry, Aziz, you have not shared your slides, so we can only see you.
Oh, sorry. Can you see it now?
Yes, yes.
Okay, sorry about that. So let me continue. So this is like a much better version of the user interface with labels that clearly define what each button does. And this is an example of what a blind person may experience when using an app that is not accessible. The idea here is that blind people use a screen reader to interact with their phones, and a screen reader, as the name suggests, would just read what's on the screen. So if what's on the screen is an icon, it needs to have an alternative text or label. Let's take an example. So this is an icon, and the label is the word help. If that label is not there, then the screen reader would just say button 1 or button 2, which doesn't help at all. And this is similar to what we may experience on the first slide. This specific issue is called missing speakable text, and it's one of the issues that we look at in this work. The motivation for this work revolves around the fact that apps play an important role in the daily life of people, especially disabled people, and having good understanding about accessibility is important to both developers and users, especially when we know that more than 1 billion people have some form or type of disability. This is more than 15% of the world population. Our study is based on the Google Android Accessibility Guidelines, which includes 11 accessibility issues. I have already explained the first one in the example at the beginning of this presentation, but unfortunately, due to time constraint, I'll not be able to go through the remaining ones. But you can read more about them in the paper. Our goal in this work is to understand the state of accessibility in Android apps through a large empirical study. And we look at accessibility from 3 different perspectives: the apps, the users, and the developers. And we realize that a holistic view would give us a much better understanding of the issue. So the first perspective is the apps. We have evaluated the accessibility of more than 1,000 apps, and for that we developed our own custom tool to automate the different steps that are required to test the app's accessibility. This is an overview of the different component tools. So the first step is, or the component is, the interaction with the app. And the goal here is just to call the different screens on the app. Next, we have the listener. So the listener is a service-only app that is running in the background to monitor everything that is happening on the screen. So every time a button is clicked or screen is opened, it performs the accessibility checks on all the elements on the screen. And lastly, we have the analyzer. So for each app, we collect the package name, the activity name, and other information as well. But the main thing is that we calculate the inaccessibility rate for each app. The second perspective is the users. So we wanted to see how users are impacted by accessibility issues. And for this, we collected all the reviews for all the apps in our data set, and we filtered the reviews that discussed accessibility. The third perspective is the app developers. So we wanted to get a deeper understanding of why developers create apps with accessibility issues. So for that, we sent an online survey to Android developers. In the survey, we asked developers about their practice of using the guidelines and also the tools for assessing accessibility, if there are any. We also asked them about the challenges that they faced when implementing accessibility based on their experience. Now we move on into the results. So we have 9 research questions. They cover the different perspectives that we discussed earlier. Unfortunately, due to time constraint, we're only going to go through 1 question for each category. So let's start with the first perspective, the apps. In this RQ, we try to find the most common types of accessibility issues. This table shows that 10 out of 11 accessibility issues are present in apps. We can clearly see that some issues are more common than others, like the first 4 on the table. So we investigated that more, and we looked at a couple of things, including Android Studio templates. So Android Studio is the official IDE for building apps in Android, and developers sometimes use those templates instead of starting from scratch. So we analyzed those templates, and we found that 5 out of the 10 templates that we looked at suffer from different accessibility issues. For instance, this screen, which was built using the tabbed activity template, has 2 accessibility issues, as you can see. So we think that the presence of these issues in the templates may have contributed towards the high number of some of the accessibility issues in apps. Now, in the second perspective, which is the developers, we wanted to get a better understanding of why apps with or without accessibility issues. And this was based on the developer survey that we sent. So this question is about the underlying reasons for why developers create apps with accessibility issues. You can see from the chart that the top reason was lack of awareness about accessibility. And this includes not actually knowing what accessibility means in general or how to apply it. The other top reasons are additional costs and also the lack of support from management, because we know they just want, mostly they want to deliver products faster. And the last perspective, which is the users, again, we wanted to understand the accessibility issues impact on users. So this question was based on the reviews we collected from Google Play. We wanted to know the accessibility issues that users complain about. So in almost half of the reviews, they discussed accessibility without specifying the exact issue. For the other half, they discussed issues related to text, image, or speakable text issue. We also found that users tend to use app reviews to communicate both positive and negative experiences with app accessibility. So in some cases, users gave a bad review and stated that they're going to delete the app as it was unusable to them. For the implications of the study, the main thing here is that accessibility issues are common in apps, and this affects individuals with different kinds of disability. The second thing here is that organizations need to pay attention to accessibility. So in the survey, most of the survey respondents told us that they did not have any accessibility evaluation as part of their app development process, and that accessibility is not treated as importantly as other aspects of quality, such as security in their organization. This issue applies to individual developers as well. The last thing is that we found that existing tools are limited and could be improved to better support accessibility. This concludes my presentation. Thank you for listening.
Thank you very much, Aziz. So no question in this Slido, but I have a question. So what kind of techniques and tools you think can help developers to ensure the accessibility of their apps? Like, should they test for the accessibility, or there should be some static analysis tools to just pinpoint accessibility issues in the past?
So there are different tools that can help developers. So it is essential that we know that manual testing for accessibility is always required, but also there are tools that could help you. And there's this official Google scanner for accessibility from Google. But I think, so as I said in the previous slide, these tools are limited. And one of the issues is that these tools may give you, even for a single app, they give you hundreds of accessibility issues. So there's a need to improve these tools, maybe prioritize those that have the high or most impact on users first, so the developers can fix those issues first and then focus on the rest. So there are tools, but I think they're limited, and that's one of the existing issues with the tool support.
Great, thank you. So the next speaker is Alan Romano from Sunny at Buffalo. So it's going to be a tool demo about visual testing of WebAssembly applications.
Hi there, my name is Alan Romano, and I'm presenting the WasmView visual testing and debugging tool. This tool is designed to show the interactions between WebAssembly and JavaScript functions through a visual call graph, as well as collect screenshots and stack traces for interactive web applications. WebAssembly, or WASM for short, is the newest standard to arrive on the web, and it's built to improve performance in a variety of use cases. This new language isn't meant to replace JavaScript. Rather, it's meant to complement it. And as such, the execution between the two functions is heavily intertwined. WebAssembly is very different from JavaScript. It's a terse, low-level language that removes the high-level abstractions such as classes and data structures, making it slower to pick up for web developers. It's distributed as a binary module rather than a script, so it's not easily readable. For these reasons, we developed WasmView to help facilitate visual testing by automatically collecting screenshots and stack traces during execution. In addition, the tool helps support development by showcasing the interaction between WebAssembly and JavaScript through the visual call graph, making it easier for developers to unravel the cross-language function calls during refactoring. Now we present a brief demo of WasmView. It's built as a web application using Node.js and is available through GitHub to run locally. In order to scan a web application, a developer enters a desired URL into the input box on the landing page and then presses the scan button. By default, WasmView scans the web app for 30 seconds. During this time, a developer can interact with the application by using the browser window that pops up. After the 30 seconds, the visual call graph is displayed. The user can view the different types of functions from both languages used in the web app, such as those defined internally in the WebAssembly module and the JavaScript functions imported into the module. In addition, the screenshots and stack traces are output in a file directory for offline analysis later. We hope that this tool will help developers maintain existing WebAssembly applications and ease the process of creating new ones. This concludes our demo. Thank you for watching.
Thank you very much, Alan. So one question I have for you is that, is it possible to change the interaction time for each application?
Yes, by default it's up to 30 seconds, but it's configurable in the source code that we provide on GitHub. So a developer could just easily modify it, and then they'd get a longer time to interact with the application.
Great, thank you. Nice work. So the next presentation is from Martin Turp from Aarhus. And it's about extracting the tainted specifications for JavaScript library. Please, Martin.
Yes, can you all hear me?
Yes.
All right, good. So my name is Martin, and I will be presenting the work extracting taint specifications for JavaScript libraries, which is joint work with Chris, Max, Anders, and Michael. So let's begin by considering the NPM system for JavaScript. The NPM system contains more than 1 million packages. There are more than 1 billion package installations taking place every day. But more alarmingly, there are at least 1,400 known security vulnerabilities in these packages. One of the most common types of vulnerabilities we see in practice is injection vulnerabilities. In an injection attack, a malicious user of a system intentionally crafts an input to the system that causes the system to diverge from its intended behavior. We say that there is an injection vulnerability whenever data can flow from an untrusted source to a trusted sink, and no sanitization or validation of the data takes place on the way. For example, if data from an HTTP request flows into a call to eval, then a malicious user could potentially cause arbitrary code execution on the system. There's also a dual problem where data instead leaks from a trusted source to an untrusted sink, which we also address in the paper. But due to the time constraints of this talk, I will focus only on the former problem. All right, so the usual solution for detecting injection vulnerabilities is to use a taint analysis. A taint analysis finds injection vulnerabilities by looking for data flow between untrusted sources and trusted sinks. A static taint analysis is often preferred because it's fully automatic and potentially sound, meaning that it will detect all injection vulnerabilities. But due to the reflective and dynamic nature of JavaScript programs, static taint analyses don't scale well for large JavaScript programs. However, a typical JavaScript application is just a set of modules where most of the modules are provided by third-party libraries. So we can achieve scalability by analyzing each module in isolation using a modular analysis. For example, the LGTM analysis. Because the module that is being analyzed may interact with other modules, it is necessary to supply handwritten summaries of how taint flows through these modules. Writing these summaries is both time-consuming and error-prone, and if summaries are missing or incorrect, the analysis may report false negatives. So in this work, we propose a solution where we use a dynamic analysis to automatically generate the summaries. Our approach is fully automatic. The inferred summaries are very precise, and summaries from multiple runs can be combined to one general summary. So to understand our approach, let's consider this example that contains an injection vulnerability. The user input variable gets its object value from a user-supplied HTTP header. The for-in method iterates through all of the property values of the user input object. For each of these iterations, the property value is passed to the callback as the value parameter, as indicated by the dotted arrow. The value is then passed to the vimref function, and vimref takes a path and a callback and deletes the file directory of the path. The getHeader method is a taint source since it reads a header value of an HTTP request that comes from the user. And the first parameter of vimref is a taint sink since the value flows into a file system API method for deleting a file or a directory. Therefore, the user can delete arbitrary files on the system by carefully crafting the HTTP request. All right, so this example uses two methods that come from external libraries. the forin method from the Lodash library, and the rimref function from the rimref library. So for modular taint analysis to detect this vulnerability, it requires two pieces of information about these external modules. So first, it has to know that the property values of user input flows into the value parameter of the callback function. A novel concept known as a propagation summary is used to encode facts like this. The flow between user input and values is encoded by this propagation summary. It consists of two access parts, and it says that all of the properties of the first parameter to the forin call flows into the first parameter of the callback supplied as the second parameter to the same forin call. The second piece of information required is that the first parameter of rimref flows into a sink. That fact is encoded by this access part. So let's consider how an analysis may infer this propagation summary and the additional sink. So there are two places in the code where values flow from the client into the library, as illustrated by the blue boxes. And we call those places library entry points. There are three places where values flow from the library into the client, and we call those places library exit points. Notice the parameter of forin's callback comes from the library, but the callback itself is in client code, so the parameter is considered a library exit point. So to infer taint summaries, we use the dynamic analysis TASER. And TASER monitors the execution of test suites and records the interactions taking place between the modules to infer propagation summaries and additional sinks. To generate better summaries, TASER is run with many different test suites, and all of the inferred summaries are eventually combined to one general summary. Once a summary is generated, it can be reused across many runs of the static analysis. So as illustrated by this figure, TASER uses a technique known as a membrane to keep track of the boundary between client and library code. The membrane grows dynamically as the analysis is running. Whenever a value passes the membrane, it too becomes part of it. For example, a callback function passed to the library becomes part of the membrane, such that the passing of the boundary that takes place once the callback is called can be tracked. Each point of a membrane is assigned an access part representing its location in the library API. These access parts are used when new propagation summaries and additional sinks are added. So TASER infers the propagation summaries by tracking how values flow between library entry points and library exit points, as illustrated by this highlighted path through the figure. The analysis also tracks how values flow between library entry points and existing sinks, as illustrated by this highlighted path through the figure. Such a flow results in an additional sink being added to the summary. So to evaluate the technique, we ran TASER on 3/3 of the top 1,000 npm packages, and we included the test suites of up to 200 clients of each package. TASER managed to extract almost 8,000 propagation summaries and 146 additional sinks, using on average 112 seconds per client. By plugging the results from TASER into the existing static analysis LDGM, LDGM was able to find 136 new injection vulnerabilities. And manual examination of 30 of the new alarms showed that only 6 of them are false positives, and that the false positives are all due to imprecision in the static analysis. So in conclusion, we present a novel technique for inferring taint summaries for JavaScript libraries. And this technique is implemented in the TASER analysis tool that monitors the execution of data flow between client and library code during the execution of existing test suites. And based on this flow, precise taint summaries are constructed using an access part mechanism for identifying library entry and exit points. And furthermore, we show that with the TASER inferred summaries, an existing state-of-the-art static taint analysis can find previously unknown injection vulnerabilities. Thank you for listening.
Thank you very much, Martin. Nice talk. We have a question from audiences. Have you compared your automatically generated specifications with manually written ones? And if LGTM generates more alerts using TASER summaries?
Yeah, sure. So a good question. Yeah, we did compare with some manually written summaries by the LDGM team. So there was a little overlap, but we used many more libraries in our evaluation than there are manual summaries available for. So there is some overlap, but generally we find way more summaries than just by manually writing them. Yeah, what was the other question?
There is no question from audience, but I have a question for you. The proposed approach and it seems to rely on the existence of the test suites. So I was wondering to what extent does the quality of the test suite, let's say like the code coverage of the test suite, impacts the effectiveness of the taser?
Yeah, it does. It does certainly affect the quality of the inferred summaries. So that is also why we use up to 200 clients for every library to get us as much coverage as possible. So our hypothesis is that that the flow that actual clients that we see during the execution of test suites of actual clients is also the flow that's probably most relevant for practical injection vulnerabilities. But we might miss some flow. That's true.
Yeah, thank you. Thank you. So our last speaker is Ilo Kim from Purdue, and he's presenting finding client-side business flow tampering vulnerabilities. So please, Ilo.
Okay. Hello, everyone. My name is Ilo Kim from Purdue University, and I'm going to talk about automatic detection of web security threats affecting online business. JavaScript web applications play important roles in the modern web environment. However, partial business logic can be also exposed to the client side, and it has created an attack surface for manipulation and exploitation. Here's an example of the threat. In order to make people subscribe to the newspaper, the New York Times uses a method called paywall. They allow a new user to see a limited number of articles for free. After that, if the user tries to read another article, they see this paywall message. But what if a malicious attacker can bypass the paywall system? Then people can keep reading articles without the limit, and the New York Times will lose their main income source. The paywall business logic is implemented in JavaScript and run in the client side without any protection. Anyone with some skills can change the code or the execution flow. We named this kind of threat to the client-side business flow tampering vulnerability. The reason why the threat is a big concern is it has a direct impact on financial loss, and also it's difficult to discover the attacks caused by the vulnerability. Unlike traditional attacks, it doesn't make damages to the backend system. Moreover, it has no immediate impact. So even if the attack occurred, the business owners may notice the attack a long time later, like when they check monthly income. Therefore, to prevent the threat in advance, we propose a semi-automated system to detect the client-side tampering vulnerability. We use a penetration testing-based approach. Our system identifies business-related functions, applies predefined tampering operations to the logic, then test the tampered execution. Let's see each procedures in detail. The first step of our system is to identify potential business-related functions. We observe mutation events on business-related DOM objects so that we can collect functions trigger the event and call stacks. After some pre-processing, we gather the functions and consider them as candidates. Our system also collects dynamic data such as control flow graph and call trace. Now we have a set of functions that might have business logic. We're going to try to alter the original execution flow for each function one by one. But before that, in order to increase efficiency, we'll give some priorities to the candidate so that we can test one that may have important logic first. So how do we know which functions are more likely to have important business logic? We get some hints from the observation during our research. For instance, the function that performs access control often has high execution frequency and also have similar source of URL with the main page. So we use the hints as features of learning-based method, then give ranks to the candidate functions based on the score. By using the candidate functions ordered by the ranking algorithm, our system generates testing inputs by traversing control flows. We call the generated testing input as a tempering proposal. The proposal contains the information that where and how we alter the original execution flow. In the testing step, the generated tempering proposal are delivered to our testing module. For each proposal, the testing module launches a web browser and replaces the recorded business operation. The web browser is equipped with our modified JavaScript engine, and it tempers with the execution by modifying bytecode as indicated in the proposal. After each test, the testing module generates results. They are checked by the tester to confirm if it successfully alters the business operation. In order to minimize the tester's effort, manual effort, we also developed test result screening method. First, if the original DOM mutation event is also triggered during the test, it means we failed to change the original execution, so we can ignore those results. And next, instead of checking every result one at a time, we gather a batch of results and group together based on similarities so that a tester can check only one result in a group. By using these techniques, we found that only around 3 testing results are needed to be checked by a tester for success cases. To evaluate our system, we select 200 real-world websites from Alexa Top 500. Especially, we select the website in the 5 categories since they use the most common business models, such as advertisement, subscription, or paywall. Here are the vulnerable cases we found from our research. The first 5 cases are found manually, and they are used for training the function ranking classifier. With the trained classifier, our system successfully found 22 more cases from the major websites throughout the 5 categories. For example, we were able to remove video advertisements from CBS and YouTube, where we could bypass the anti-ad block techniques from CNBC or Seattle Times. Also, there is a point reward website, inboxdollars.com. They give cashable credits when a user watches a video advertisement. We were able to repeat the credit rewarding operation without watching the ads. Here is an experiment result showing the efficiency of our function ranking and the test results screening. The blue bars show the numbers of tests performed until we find vulnerable locations. As a result, almost in every case, our system successfully found a vulnerable location within 20 tests, and it's about 14 tests on average. Next, the orange bars indicate the number of results after the event-based screening, and the gray bar shows the final result left after the clustering. It shows that the screening method successfully reduced the result. For example, in the case 16 in the middle, our system performed the 50 tests to find the vulnerable points, but we only had to check 3 results manually. Our system will be publicly available soon in the repo. And thank you very much, and I'm happy to have the questions.
Thank you very much, Ilek. So we have a question from the audience. What was the size of the training data set for your classifier? And can you elaborate more about the properties of the data set?
So in order to train the function ranking classifier, we use these first 5 cases we manually found. And we have, based on our observation, we picked like these 10 features for the classifier. But after our feature selection process, we found the highlighted 5 features are related to the vulnerable points. So we use them to train the classifier.
Okay, so I also have a question for you. So did any of these, like the tempered execution cause any like adverse effect? For example, breaking the functionality of the application, the system you were trying to penetrate?
Yeah, during the test, if the tempered execution break the original execution, then it means we failed the test. So it belongs to the tailed test cases. And finally, the tester, I mean the human, need to check the successness of the test.
Okay, thank you very much.
Thank you.
So yeah, so we're done with this session, and thank you everyone for joining the session and supporting the presenters in the last session of the last day of XP. Thank you.